Welcome everybody. As she said, my name is Kyle from Star Seekers with Men on the Lake, Parks and Rec Department. We launched Star Seekers about a year ago, we'll say, sometime last March, April timeframe. Not to focus on the eclipse, but really to offer the community of Men on the Lake some additional activities to do that might be fun or interesting that have not had any light before. So that's our origins, and now with the total solar eclipse, we're really focusing and doubling down on that. So today's presentation is going to be a celestial dance of light and shadows. So we're going to focus on the moon a little more intensely than last presentation, as we do have a lunar eclipse coming up on March 25th. So we'll talk about that, and then we'll get into eclipses, telescopes in general, if anyone is interested in learning about that. And then we will double down on the safety, the countdown to the solar eclipse, and then some local activities that are in the area. So to start off, we will go to the moon, which is our closest celestial neighbor. All right, so the moon. The moon itself is called simply the moon because people did not know that other moons existed at the time, until Galileo discovered 4 moons orbiting Jupiter in 1610. So in Latin, the moon was called luna, which is the main adjective for all things moon related. That's why it's called lunar. So like a lunar eclipse, and you'll see other celestial, like in print or articles, they'll reference lunar moon, which sometimes is like a double negative, like an ATM machine. It's like saying the moon. So yeah, so that's how the moon got its name. It is Earth's moon is the brightest and largest object in our night sky. It makes Earth a more livable planet because it moderates our planet's wobble on its axis, leading to a relatively stable climate for us to grow and thrive. It also does cause our tides, which creates a rhythm that has guided humans for thousands of years. The leading theory of the moon's origin is that a Mars-sized body collided with Earth about 4.5 billion years ago, and the resulting debris from that collision accumulated to form our only natural satellite, and the moon is 239,000 miles away from us. So that newly formed moon was in a very molten state at the time, but within about 100 million years, most of the global magma ocean had crystallized. So there were less dense rocks floating up, which formed the crust on the moon. The Earth's moon does have a core, a mantle, and a crust, as we just said. And that crust on itself, they have found the rock has crystallized to form what's called they call it moon glass. So it is where the temperature gets so hot, either from the original cooling of the magma or from the sun having solar supernovas. When it hits the moon, because of its lack of atmosphere, it gets really hot really quick, which then turns that rock that is on that crust into a layer of glass. So sometimes astronauts will see something shiny, and then NASA thinks that's just a high concentration of moon rock that was turned into glass. So with too sparse of an atmosphere to impede any impacts, the moon does see a steady rain of asteroids, meteors, and comets that strike the surface, leaving all of the craters behind that you can see from your naked eye. And so over billions of years, these impacts have ground up the surface of the moon into fragments ranging from huge boulders to really, really fine powder. Nearly the entire moon is covered with a rubble pile of like charcoal, grayish, powdery dust and rocky debris, which is called the lunar regolith. And beneath a region of fractured bedrock is referred to the, I always get this one wrong, megagrolith. So yeah, the moon does rotate at the same rate as it revolves around the Earth, so that is called a synchronous rotation. So the same hemisphere faces the Earth all of the time. So some people you may have heard say like the far side of the moon, that is just referencing the hemisphere of the moon that we cannot see here from Earth. So that dark side is a little misleading, but just references our viewpoint of the moon from Earth. And then as the moon does orbit Earth, different parts of sunlight or darkness at different times encounter the moon. So that changing illumination is why, from our perspective, the moon goes through different phases, and we'll get more into phases later. And the moon does make a complete orbit around the Earth in roughly 27, some other studies say 29 days. So it's somewhere in that range, which is why you do have 4 lunar cycles that you see reoccurring every month. All right, so getting into moon phases. So the moonlight that we see on Earth is only the sunlight from the sun that is reflecting off of the moon's grayish white surface. The amount of the moon we see illuminated does change over the month, which is called the lunar phases, because the moon orbits Earth and the Earth orbits the sun, so everything is all moving at once. As the bright parts of the moon appear to change shape during the month, that is signaling that each stage of change is called a phase. So as you can see up here, goes through the different stages of the moon. Sometimes people think, oh, a new moon, it's going to be the bright one. Nope, new moon is actually the one that you cannot see here on Earth, as we are blocking. The moon is essentially in front of, this is the sun, the sunlight hits the moon, and then the Earth is behind the moon. So it is just, we see the moon as black because we're not seeing that illuminated side. So when the sunlight is illuminating only the moon's far side, the side that we can't see directly here from Earth, that is the new moon. And then when it illuminates the moon's near side, which is the side that always faces Earth, is called the full moon. And then the rest of the month we see a different amount of the daytime side of the moon each day. So the continually changing views of the sunlit part of the moon are the moon's phases. So the 8 lunar phases are in order: new moon, which is on the far right there, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, third quarter, and waning crescent. And this cycle does repeat about once a month. From this NASA site, they say every 29.5 days. And then for this upcoming eclipse, we have the last quarter. So if you see here where the last quarter is on that, it's really going to be essentially I think it's the top one where it says first quarter, is on March 3rd, and then we're going into the new moon on March 10th. The first quarter is on March 17th, so on St. Patrick's Day. And then the full moon is on March 25th. And you can only see any type of lunar eclipse when there is a full moon. Otherwise, things do not align, and it just looks like a normal moon phase. All right, so there are technically 3-ish kinds of lunar eclipses. So one is going to be the penumbral eclipse. So that is the one that is occurring later this month. And that occurs whenever the Earth does pass between the moon and the sun, such that it obstructs the sun's light and casts a shadow onto the moon's surface. So again, that's happening on March 25th this month. Now that is at 3:21 our local time. So that is a go to bed, set an alarm, and get up if you want to see it type of time. And that is all for the entire United States. And it starts, I believe, around midnight and does last through, I think it's just shy of 5 a.m. And then they also have the umbra eclipse. So that is when the moon is in the complete darkest shadow of the Earth. And then you have a total lunar eclipse, which is where the entire moon passes through the Earth's umbra shadow. So there's no little bits or pieces. It is entirely covered in that. And when the moon is in a total lunar eclipse, the moon has a very, very reddish hue, similar to a sunset. We see red sunsets here on Earth because red is the longest wavelength of light, so that is still reaching to us. So when the moon gets in that shadow of the Earth, the sunlight bends around Earth's atmosphere, and the longest rays of that is the red light, which is why the moon does appear red. So then going over this just in a little more detail, we have the outer part of the Earth's shadow, as you can see in that diagram, which is that light gray. So that is the area in which the moon will be entering this March. So that, again, is called the penumbral. And then the moon itself, like looking from the naked eye, the brightness of that will be greatly reduced as it is less strongly illuminated by the sun due to the Earth's shadow, but we will still be able to see the whole of the moon's disk to some degree. The effect of this is only perceptible to those with a very astute vision or carefully controlled photographs. However, for this particular one, the moon will be 95% covered by Earth's shadow, and it will last roughly 280 minutes, so just over 4.5 hours from beginning to end. The next one is going to be occurring in September of 2024. And for that one, people in the Americas, Antarctica, and the Western Indian Ocean, Middle East, Africa, Europe, Atlantic Ocean, and Eastern Polynesia will see the shadow of a partial lunar eclipse. Again, that will happen overnight, September 17th into 18th. And there will be a steady golden light as well, people may notice, near the eclipsed moon, and that will be the planet Saturn. So if there's any Saturn fans in the crowd, it'd be a great time to get out your telescope as the moon's sunlight will be dimmed and Saturn will be more easily to recognize in the space. So the whole half of Earth facing the moon, that is the whole half of Earth that is in nighttime, will see that lunar eclipse. And of course, the lunar eclipses are safe to view with the unaided eye. You don't need anything special like during a total solar eclipse, as we're looking at the reflection of the sun on the moon, so there's enough distortion there that it does not hurt our human eyes from our planet. So you can use binoculars and telescopes if you want, just to enhance that, but it is a little tricky during some of these because you'll just notice the moon getting darker. So to me, for this type of eclipse, the cool thing is having a telescope or binoculars when it starts, because you can then see the Earth's shadow start creeping over the moon, and you get to see where it gets darker. So you're kind of following it along, tracking that motion of our space objects. So why are moving into kind of like the main event for later this year of why are total solar eclipses so rare? They are so rare because in order to view a total eclipse, you must be in the path of the eclipse umbral shadow, and that shadow is only 100 miles wide. So the shadow only covers 1% of Earth's surface. And as we know, Earth's surface is primarily water, so it's even rare when it goes over, a body of land on our planet, and then you have to hit the right time and the right weather. So it's a very rare event that is coming up here. And some fun facts about the moon. When you are inside of an eclipse, the temperature, light temperature of the moon, forget the eclipse part, but yeah, light and dark side of the moon ranges from 260 degrees all the way down to negative 280. The moon's diameter is about 2,100 miles across, and the average distance from the Earth to the moon, 238,855 miles. And you'll notice that in many science articles, some of these numbers are slightly off. That is just how science is. We have not yet perfected down to that precision level yet. So you'll see like the Earth and the moon cycles, sometimes they ebb and flow depending on where you're calculating your averages from, or even for the moon phases, 27 days versus like 29 and a half days. And that will be consistently changing over time because the moon is moving further away from Earth every year, which does have a major impact here on Earth. Not so much that we're going to see currently, but maybe in 100, we'll say 1 million to 100 million years is when we'll really start to notice that, because then we won't have tides anymore. The moon will be too far away and too weak to actually have tides. So we're going to see some craziness, whoever is around at that point. And just a cool picture of the Earth from the moon. And now we'll get into the juicy part of this, eclipses in general. All right, so as you can see here, there are different types of eclipses that were mentioned, solar eclipse and lunar eclipse. So solar eclipse is when the moon gets in the way of the sunlight that is hitting Earth, and then a lunar eclipse is when the Earth gets in the way of the sunlight that is hitting the moon. And so when we have a total solar eclipse, that does happen about every year and a half somewhere on Earth. And then a partial eclipse is when the moon doesn't completely cover the sun, and that also happens at least twice a year somewhere on Earth. Again, the Earth is 71% water, so the chances of you being in a spot that happens is very rare. Our moon is the perfect size and distance away that it's one of the only celestial objects that we know of that actually will see a full total eclipse, just due to the size and its space away from Earth and into the sun. Granted, with the James Webb Telescope, I'm sure we'll be finding more of these out in different constellations out in space, but as of right now, it is one of the rarest things, and that is why people are always questioning, how did the moon get formed? Why is it here? Then we've had recently had spacecraft crash on the moon that made the moon ring for, I think it was like weeks. So now scientists are looking into how hollow is the moon and what caused that? What's the makeup under that crust? And then during an annular eclipse, the moon is a bit closer to the sun. So during one of those, you see the edge of the sun disk being uncovered. So the result looks like a bright ring of fire in the sky. But during April's total solar eclipse, the sun's disk is completely covered, allowing the outermost layer of its atmosphere, the corona, to shine, really see that fire in the sky behind the moon. So two things that need to occur at once in order for you to see a solar eclipse. One is the sun, the moon, and the Earth need to be in an exact straight line, with the moon between the sun and the Earth, and you need to be standing in the correct spot on Earth. But not everyone experiences every solar eclipse, so getting a chance to see it is rare. The moon's shadow on Earth isn't very big, like we said, only about 100 miles wide at its darkest totality point. And then so you have to be on the sunny side of the planet when it happens, and you also have to be in the path of the moon's shadow. So on average, the same spot on Earth only gets to see a solar eclipse for a few minutes about every 375 years. So truly, it's a once-in-a-lifetime event for most people, if they're lucky. And then for a lunar eclipse, has to happen at night under a full moon, and that's when that full moon does fade away and Earth's shadow covers it up. So again, that is on March 25th this month. The moon can also look reddish, as we went over, because of those sunlight rays. And during a total lunar eclipse, the moon is shining from all the sunrises and sunsets occurring on Earth. And so this is just a close-up diagram of what happens to Earth when we do have a total solar eclipse. So the moon gets in the way of the light of the sun, and just like we were talking about earlier with the umbra and the penumbra, both Earth and the moon do create an umbra and penumbra on each other. So during a total solar eclipse, we are going to be in the path of the umbra, which is that darkest point. So the sun and the moon, they're not really the same size, of course. The sun is 400 times the diameter of the moon, but it's also 400 times further away from us. So this is that special relationship between the two in terms of size and distance that makes the sun and moon appear to be the same size in our sky to us. So it's one of those wonderful, miraculous coincidences. And currently, Earth is the only planet in our solar system with a moon the proper size and distance to cause a solar eclipse. The motions of the sun, the moon, and Earth, bringing those three bodies into alignment 2 to 4 times a year, but a perfect alignment gives us that total solar eclipse, only occurs about once every 18 months. So during the day, as the moon passes in front of the sun, it begins to cast a partial shadow, the penumbra, onto Earth. And then at the height is when we're going to be entering into that umbra shadow, which is when the sun's light is entirely blocked. The moon's darkest shadow hits only a small part of our planet, however. So the perfect alignment of the sun and the moon is visible from a limited region of Earth. The area where you can see an annular or total eclipse is never more than 167 miles wide and is usually much less. Outside that area, you'll see only a partial eclipse or even nothing at all. And then the area on Earth where a solar eclipse is visible, it's not static, because the moon and the Earth are not fixed objects. The moon orbits the Earth and the Earth orbits the sun. So in addition to spinning on its axis, you have all of those compounding that make it truly a rare event. So that is the path of totality that we will be entering into on April 8th. And so although total eclipses do happen regularly, the path of totality is extremely limited. So if you stood in one place on Earth and waited to see a total solar eclipse, you could wait anywhere from 300 to 375 years or more in order for that to happen. So this is just a diagram of what the Earth looks like whenever you have the moon getting in the way of our sunlight. So this is obviously not, this is one that did happen, and this is where it started on the west coast and worked its way eastward. I would say maybe like southeast. So yeah, this time though it's going to be coming in the opposite direction. It's going to be coming from the southwest and heading to the northeast. So that is going to be the exciting time for us. And during a total solar eclipse, the local temperature when you are in that totality does drop about 20 degrees. So not only do you visually, see everything get darker, but you also feel it. Temperatures get cold, animals will start acting a little crazy, and it's a cool event. And then 3,000 miles, what is that? It's the distance of a partial solar eclipse can be seen from. And then 600 million years, solar eclipses end due to the Earth slowing rotation and the moon distance. But they are saying that the Earth itself will see different like environmental signals much before then. That is when solar eclipses will end. But we will feel the impact of the moon getting further and further away from us. But not anybody in this room unless there's some crazy scientific advancement. All right, moving on to telescopes now. Luckily, like she said, we have a clear sky. We've been trying to have some star viewing for the past 3 or 4 events, but it's always been rainy or cloudy. So I'm very excited to get out there after this. But to give you a brief little history of telescopes. So they were invented in the early 17th century and played an important role in advancing our understanding of Earth's place in the cosmos. The first telescope was created in the Netherlands in 1608. And there were spectacle makers, Hans Lipsche and Zacharias Janssen and Jacob Matthias. They all independently created telescopes. So it was almost like the technology at the time was so widespread, you had different people in different parts, working on that same science and arriving at the same conclusion in a relatively the same amount of time. So this telescope did emerge from the tradition of craftsmanship and technical innovation around making glasses or spectacles, and developments in science of optics trace back through Roger Bacon and a series of other Islamic scientists, in particular Al-Kindi, which was in 801 to 873, and then also Ibn Sal and Ibn al-Haytham. Early telescopes, though, were primarily used for making earthbound observations, such as surveying, the topography of the Earth, as well as to aid in military tactics for planning battles and just being strategic in how they were going to move forces forward. And then Galileo, he definitely revolutionized it by turning it to the heavens. So he was part of a small group of astronomers who turned the telescope towards the heavens. After hearing about the Danish perspective glass in 1609, Galileo constructed his own telescope, and he subsequently demonstrated that same telescope in Venice. And after that demonstration, he really earned a lifetime lectureship, so almost like equivalent to being a tenured professor in modern day. And after his initial success, Galileo focused on refining the design of the telescope, and it developed an instrument that could magnify 8 times and eventually up to 30 times. And then these new observations, were not exclusive to Galileo, but the story of Galileo and the telescope is a powerful example of the key role that technologies play in enabling advances in scientific knowledge. So with that said, the telescope isn't the only technology at play in this story. Galileo definitely used, the printed book as well, and design of prints in his books to present his research to the learning community. This is not a story of a lone thinker theorizing and piecing together a new model of the cosmos. In fact, it's quite the opposite, as an array of individuals in the early 17th century took the newly created telescopes, pointed them towards the heavens, and really started writing everything down. However, Galileo is the one that understood the significance and importance of the observations, and he was the one who wrote it down, which allowed them to be dispersed amongst everyone, which really ratcheted up everyone's understanding of space. And then in March of 1610, he published the initial results of his telescope observations in the Starry Messenger, which is a short astronomical paper, and that traveled to the corners of the Earth. All right, so as you can see here on this little word map, there are a lot of different types of telescopes. I'll just go over the three main kinds that you will typically encounter. So one is a refractor telescope. So that is the typical design of what you think of when someone says, hey, I'm bringing a telescope. First thing your mind goes to is a tube, sometimes maybe on a tripod, and that is what a refracting telescope is. So it is made of a long optical tube with a convex glass lens at the main opening. So the light enters the telescope through the lens and then exits the telescope through the eyepiece for viewing. The glass lens refracts or bends the light so that it reaches a focal point. And the size of the lens, known as the telescope's objective, determines the amount of light that the telescope can collect, which is also known as the aperture. So if you are out there shopping for a telescope, I highly recommend having a little cheat sheet because they use words that we don't normally use in everyday life. And then you have to really compare the aperture, the type of telescope, and then there's some other things we'll get into as well. So refractors do come in many varieties, so they can be optimized for different use scenarios, including astrophotography, research, or just visual astronomy. And then you get into the reflector telescopes. So a reflector telescope introduced a new concept. It's using mirrors as the primary way to gather light and redirect that light into a focal point. So unlike refracting telescopes, reflectors do not utilize a glass objective lens. Instead, they use a large curved mirror that is situated at the base of the telescope. So that was known as the primary mirror. So the diameter and size of that mirror for reflectors is known as the aperture, which plays a role in bouncing the light rays back towards one or more of additional mirrors inside that telescope until the light eventually exits through the eyepiece. So as you move towards larger aperture sizes, so larger diameter mirrors, the mirrors are much less expensive to manufacture than high quality glass. So that's what makes it possible to build telescopes that can really collect a lot more light without a dramatic increase in cost. And then refractor telescopes have many subtypes which do differ from each other, mainly due to the number of mirrors, the shape of those mirrors, and other small details. So that could be a Newtonian telescope named after Isaac Newton. There's the Dobsonian telescope, which is the compound, or there's also the catadioptric telescope, which was more of a compound reflector. So as light comes into a telescope, it'll hit a main mirror, and then some of these other ones have side mirrors, so that main mirror bounces light off of here, which could then bounce back to a fourth mirror, which then will bounce the light into the eyepiece. And then you have the Cassegrain telescope. So this is a really sharp, it produces high contrast images. It's really a good choice for more of the intermediate to more experienced observers. And that type of telescope, it is a reflecting telescope, but it does also have a combination of primary concave mirrors and secondary convex mirrors in its design. So the classic Cassegrain telescope, it's a parabolic primary mirror. It has a hole placed in the center. Well, it may seem strange, why is there a hole in that mirror? But the incoming electromagnetic waves are actually captured by the mirror's edges and redirected to the hyperbolic secondary mirror where they join. So the light or a wave is then refocused back towards the hole where it converges to a focal point. and then that focal point is what is allowing anyone to see the image that is coming through. Then there's also something called a folding technique, which is a very compact design, so you don't have to have large, bags, cases, anything like that to move these telescopes. They're typically the ones that are smaller, similar to that, where it's like shorter in terms of tube length, but definitely wider in diameter. And there's a whole host of different reasons why someone may choose one type of telescope over another. It could be price and affordability, because the reflector telescopes are less expensive for the larger aperture sizes. For smaller telescopes, refractors still offer a good value though. Then you have maintenance and ease of use. Again, we're going to go with the refractors because the reflectors require more maintenance of the internal. You have size and portability. Probably, depending on what you're using it for, large refractors are more compact. Large reflectors are more compact than refractors, and you can achieve the same, aperture size that way. You have optical performance and clarity. So depending on what you're looking at, either a reflector or a refractor, both really do offer a good image with those, high quality images. Just depends on what you're really trying to look for. If you're looking for more like deep space versus local planets, each one might offer slightly different, points there, if you will. And then for deep sky, when you're trying to look at far away other galaxies or nebula, that is definitely going to be the reflectors, because the large reflectors make it possible for the average astronomer to view distant galaxies, nebula, or star clusters. So yeah, lots and lots of different types of telescopes, lots of different operating models as well. Now they have telescopes for about 1200 where you can program it to a point in the sky and it will move with the Earth. So you never actually have to refocus and readjust the telescope, which is quite nice. And you can also put in the coordinates of anything you want to see. So you know where Saturn is, you have the date where you're located, and you would put in Saturn, and the telescope would automatically adjust to find where Saturn is in the sky, if it is up in the sky and not below us. So with that, you have different lenses, magnification, and mounts. So lenses are the eyepieces. You'll see them, having different numbers. So like 10 millimeter, 5 millimeter, 20 millimeter. The smaller the number, the higher the magnification. So it's best to start off, with I would say if you're buying it, one low, one medium, one high. But when you're operating a telescope, you want to start off with the higher number. That way you can focus on whatever object you're trying to see. And then you can always switch out your lenses to have more magnification from that point. Mounts are a very key piece when you are looking at a telescope. Most of the mounts nowadays are that azimuth mount, and that just makes your telescope stable. So if you just have a tripod with a flat telescope, you're constantly have to be lifting the whole thing up and moving it or manually adjusting the telescope, which makes things really hard in order to refocus on whatever celestial body that you're looking for. So a lot of these mounts, stabilize the telescope and have an easy way, like dial knobs that you can turn to just slowly move the telescope left or right or up and down, which allows you to really maintain that focus of whatever object it is and also quickly, track it. So that, like I said, the Earth is moving, the objects in space are moving, so just a little turn will allow you to keep that in focus throughout the evening. And then you have your magnification. So of course, right, higher is the better. Not all the time. It really depends on what you're looking for and what you're looking to get out of a telescope, I would say. So any magnification above, 50 per inch of aperture is really useless. And this is what I mean by if you go out and get a telescope, it's best to have a cheat sheet of like, what does aperture mean? What type of telescope am I looking at? What type of magnification does it use? Because every little thing is going to be different, which makes getting a telescope kind of daunting because you don't know if you're going to be getting the right one or the wrong one. But there are plenty of different websites and also YouTube videos that go into, which one to get for you with what you want to get out of it. All right, so total solar eclipse viewing safety. This is crucial for safety. So when you view the sun, through eclipse glasses or any type of handheld viewer, that is definitely preferred. Eclipse glasses, they're not like regular sunglasses, so please do not try to use regular sunglasses, no matter how dark they are, or how polarized, or some special coating. It just is not the same for viewing an eclipse. Don't look at the sun through a camera lens, telescope, binoculars, or any other optical device while wearing eclipse glasses or using a handheld solar viewer. The concentrated solar rays will burn through the filter and cause serious eye injury. So essentially, if you're looking at the sun through a camera lens, telescope, you're magnifying the sun's energy and focusing that energy down to a smaller point. I don't know if any of you as a kid had a magnifying glass and would hold it up and burn a spot on a leaf. Essentially, that's what you're going to be doing to your eyes if you're using any of these other optical elements to view the sun besides using actual solar eclipse glasses just by themselves. You can view the eclipse directly without proper eye protection only when the moon completely obscures the sun's brightest during the brief spectacle period known as totality. However, because totality does not last long and people are not timing it, it is still not fully recommended to do that. You'll see the sun start coming. By the time you start seeing the sun start to peek out, it's already hitting your eyes and causing damage. So as soon as you see, a little bit of the bright sun appear, that's when you should immediately put it on. I know most people do like to sneak a peek, but truly safety is paramount here, because there are definitely horror stories when I was trying to put together this presentation of people getting injured and they didn't even know it. And then all of a sudden they had the spots in their vision that they could not see in anymore. And then this is the brochure that is on the back table over there. Kind of summarizes all of the safety tips here for viewing. So it goes over glasses, what it is. It's a nice little recap of everything. Highly recommend grabbing one on your way out. All right, so that was a little bit of safety, and now we get into the fun stuff. The countdown until the total eclipse. So for where we live in beautiful Mentor on the Lake, Ohio, the partial eclipse will begin at 2 p.m. And then it'll move into totality at about 3:14 p.m. with the maximum being at around 3:16, and then totality ends at 3:18. So totality from 3:14 to 3:18, you only have a brief 4 minutes there to really experience the full of it. But the partial does not end till about 4:29, 4:30ish. So between 2 o'clock in the afternoon all the way to 4:30, with, we'll say, 3:15 to 3:18 is when you're going to experience the darkest part of the total solar eclipse. And then some fun facts here again. So in 2099, it's when we will see our next total solar eclipse. The speed of the moon's shadow moving across Ohio. As you can see there, it is very fast. So that's why the totality time is only 4 minutes, because it is coming in as quick as it is getting out. The duration, 3 minutes and 58 seconds. So that is when you have to be in place, ready, glasses on, ready to watch that. And then here are just some local activities that are happening around the area. We have this event today. We're going to be doing the Make Your Own Viewer on the 6th. So that is what Star Seekers and Mentor Public Library are putting together as a joint effort. And then elsewhere in the community, there's lots of other events happening. So I would say these are some of the websites I found that were most holistic and captured most of the events. These are some of the ones that are happening locally, in Willoughby, in Fairport, in Mentor, Lake Metro Farm Parks as well. Again, more fun facts here. So this is what we are expecting. It is going to get busy around here, so plan now, plan early. We do expect a high influx of people coming into our state in order to, observe the total solar eclipse. We do have a 60-70% average cloud cover in April. So if anybody knows any rain dances or anything like that, please engage in that now. so we have a clear sky. And this is due to the path of this totality. We have close to 32 million Americans living in that path, which is one of the highest we've had in the past. I think it was like 6 total eclipses for us, not counting the rest of the world. So thank you. Thank you for your time. And we're going to be, again, doing some star seeking right out there. Give us a few minutes to kind of get the telescopes set up. The sun is still going down anyways, so we have some time. But we are going to be trying to see what we can see in the night sky. And we are in a new moon phase, which means the sky will be extra dark, so we can focus on, hopefully, some planets and other elements like that.
Thank you.
Yeah. Cool. Thank you, guys.